Alright, so the first type of reaction we're going to talk about are precipitation reactions. This is going to lean really heavily on the solubility rules in table 7.1. I don't have a printer, so I wrote them down by hand. I'll pull the rules over as needed, but feel free to just look at them in your book, or I will also have a link to that table in the supplementary materials for this week's lecture material. So, a couple places you can look at it. So you don't have to look at my terrible handwritten version, but I did break it down nicely. Like, I numbered the rules, whereas the table just makes a table, doesn't number anything like that. Obviously, mine would be better. If you could have the computer formatting and my idea of numbering, it would be great. Anyway, what is a precipitation reaction? Let's start there. So it is going to lean on those solubility rules, which we'll talk about in a minute. But what is the signature of this reaction? So like a combustion reaction had a kind of a signature profile. It was you were lighting something carbon-based on fire. That was the combustion of a hydrocarbon. So what is a precipitation reaction? Well, a precipitation reaction is when you have two ionic compounds that are dissolved in water, and if you mix them together, a solid forms. Okay? And then it settles to the bottom. And so a precipitation reaction results from a solid forming after mixing two dissolved ionic compounds. So you take two aqueous solutions, they're going to be dissolved in water, you mix them together, and something is no longer soluble in the water. Okay, so you go from two soluble compounds. Those words are a little too similar apparently. Two soluble compounds, you mix them together, and you get one that is insoluble. It does not dissolve in the water. So this is all going to be water-based chemistry. This is all going to be in an aqueous environment, right up until that solid crashes out of it. And that's called a precipitate, by the way. But we'll get to that in a second. And that's where the name comes from. So first off, let's talk about the solubility rules and make sure that makes sense. So some ionic compounds dissolve in water, and some do not. And so they're called soluble salts and insoluble salts. Soluble means it dissolves in water. And insoluble means it does not dissolve in water. Okay, so that's what we're talking about here. And so if you have an ionic compound and you see any of the group 1 cations, so if you see any of those first column metals being the cations, so if you see like sodium something or lithium something, potassium something, it's going to be soluble. If you see ammonium something, it's going to be water soluble. If you see something chloride or bromide or iodide, it's going to be soluble, unless it's like silver chloride, or, I forget whatever the name of that is, chloride. I don't use that ion a lot. Technically it's polyatomic. Or, lead 2 iodide, like that would not be soluble. So, some of these rules have exceptions. Now here's the good news. I don't expect you to memorize solubility rules. Look at that. There's rules and exceptions and all this stuff. What I expect you to be able to do is use this table as a resource to understand this table as a resource and be able to determine if an ionic compound is going to dissolve in water or not. That's where we're going to start. And we're going to build on that understanding later on in this video. Fluoride is a little different. So generally a column has similar chemical behavior. Fluoride's a little bit different from its neighbors. It's basically the same, but it has a few other exceptions as well. Or actually has different exceptions. So it's generally soluble just like them, but different exceptions. So group 2 cations, so if you see like beryllium fluoride, magnesium fluoride, calcium fluoride, it's going to not dissolve. It's going to be insoluble. Or if you see lead 2 fluoride or iron 3 fluoride, it's not going to dissolve in water. Alright, polyatomic ions, acetate, bicarbonate, which is carbonate with an H on it, nitrate, and chlorate. These are all generally soluble, no exceptions. Just like rule 1 here had no exceptions, no exceptions. So that's nice. Sulfate, one more polyatomic anion, generally going to be soluble unless it's like silver sulfate, barium sulfate, calcium sulfate, blah 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 sulfate. I should have really looked that one up before I made this video. Lead 2 sulfate and strontium sulfate. So hey, if you don't remember all the names of polyatomic ions, that's okay. Just get them down eventually. I'm rounding into 20 years and I still apparently don't remember that one right now. So it happens. Insoluble. So the first 5 rules here were things that are generally going to dissolve in water. This is where these rules get a little bit tricky, because the whole perspective shifts. And now it's like this stuff doesn't dissolve in water unless it's paired with something that makes it actually dissolve in water. So these are things that are generally not going to. So carbonates tend not to dissolve in water. Chromates tend not to dissolve in water. Phosphates are not very soluble. Sulfides are not soluble. Now the exceptions are basically all the stuff from Rule 1. Group 1 cations and ammonia. Which, by the way, if you look at the table, you won't see ammonium up here. It's just another way I'm better. Okay. So the last rule, the hydroxide polyatomic anion. Those are generally not soluble unless they're paired with group 1 cations or barium. So, yeah, that's pretty much it for the rules. So let's make sure that these make sense. Okay, let's practice this a little bit. So, because this is going to be very key for what we talk about moving forward in the video. So I'm going to write a list, and you tell me if it's soluble or insoluble, alright? And how are we going to do this? We're going to apply the rule book, okay? So, you knew it was going to be the first example, come on. NaCl, alright? Barium sulfate. Iron 2 fluoride. Copper 2 sulfate, aluminum phosphate, sodium carbonate, lead 2 carbonate, and magnesium hydroxide. Look at that, old hat, right? Names, formulas, you totally got it. That was last week. No problem. Hopefully. Alright, so, which of these are soluble, which are insoluble? Well, we'll start with NaCl. Look at that, it's got a group 1 cation, right? Sodium is in group 1. It also has chloride, and it's not paired with one of the exceptions. So this is soluble. Rule 1 and 2 both say it's soluble, so not bad. So it must be pretty soluble. Barium sulfate. Alright, let's see. I don't see anything about barium anywhere in here, but sulfate shows up. So these are generally going to be soluble, except if it's, boom, oh, there it is. This is going to be insoluble. It's an exception to the rule. So generally a sulfate would dissolve in water, but that barium, when it's paired with it, not soluble. FeF2. Good old FeF2. Alright. So, let's see. I don't see anything about iron. What about fluoride? There's fluoride. Exceptions, group 2 cations. Iron is not a group 2 cation. It's not magnesium or, beryllium or anything like that. It's not lead 2. And, did I get tricky on you? What do you think? You think this is going to be water soluble? What is that? That's the 2 plus, right? Because I've got 2 minuses here. So that's not iron 3 plus. So it's soluble. I might have got a little cute there. The charges matter. Like when they say iron 3 plus, they mean iron 3 plus, not iron 2 plus, iron 3 plus. So this is not an exception to the rule. So generally F minus is soluble, therefore this is soluble. Copper 2 sulfate. Sulfates are generally soluble. I don't see copper 1 or 2 in the exceptions. This is going to be soluble. Alright. Aluminum phosphate. See, I don't see anything about aluminum, but there's phosphates. They're generally insoluble unless they're paired with stuff from, sorry, let me move that up, stuff from the first rule. So it's not a group 1 cation, it's not NH4+. Aluminum is none of those. Therefore it is insoluble. Because remember, this is going to be insoluble. Unless there's an exception. Sodium carbonate. I bet you're so good at rule 1 you already know the answer to this. But just to be safe. So carbonates would generally be insoluble, except, you know, the rule 1 stuff always wins, right? So it's a group 1 cation. You see sodium on something like that is soluble. You've been doing this for, you know, I don't know, 5 minutes. You've already mastered it. Good job. Lead carbonate. We'll talk about this one in a second. There's a reason I put it up here specifically. Carbonates are generally insoluble. Lead is no exception. So this is insoluble. And this is how the city of Flint, Michigan used to control the lead levels in their pipes. So they use lead in their pipes, which everyone did ever since the Romans. It's only recent that we stopped doing that. And what they would do is have a nice lining of lead carbonate that was insoluble to keep the lead from dissolving into the water. The problem is they went bankrupt. The city became no longer responsible for their finances. The state took over, and the governor at the time, who's not the governor now, decided that it was appropriate to save, I think it was like $30,000 a year, something like that, on water by just pumping it straight from the river nearby instead of getting it pre-treated from the lake via Detroit. And so when they pump it straight from the river, the pH was different and it dissolved. When you change the pH, suddenly this became soluble. And so it put all the lead in the water. And now you're looking at multi-billion-dollar repair if it's ever going to be fixed, which it still hasn't, by the way. So that was not a decision made by the people of Flint, Michigan. And their infrastructure was not any different from anyone else in the state of Michigan either. And it was a blatantly obvious chemical just fact that that was going to happen. And the state employees ignored all the warnings from the people that were telling them. And they just did that. So it wasn't an accident. It was pretty much intentional, as far as I'm concerned. From a chemist perspective, that was an intentional act by the state of Michigan to essentially poison the city's drinking water. So, magnesium hydroxide. We'll just keep going down the list. This one doesn't have an interesting history of causing billions of dollars in repairs, but it is used in antacids, so that's cool. All right, hydroxides are generally insoluble. Magnesium is not barium. Magnesium is not group 1. This is insoluble. Okay, so there it is. Hopefully that's making sense. All we're doing is just applying the rule book. So these rules are just for ionic compounds and whether they dissolve or not in water. And so it's kind of a little rundown on that. So, what about precipitation reactions? Well, if we have some dissolved sodium chloride, which our rules say is going to happen, and we have a dissolved solution of silver nitrate, which our rules also say will happen. So whereas nitrates are generally soluble, no exceptions. So silver nitrate is going to dissolve. And here's what we do. We switch the pairings. So I need to have different products than reactants, right? And so I go, oh, okay, well, I'll have AgCl, and I will have NaNO3. And now I got to figure out what the phases are based on my solubility rules. So AgCl, silver chloride. Chlorides are generally soluble unless they're paired with silver. So that means we've got a solid. Okay? NaNO3, Group 1 cation, also NO3. So rule 1 of 4 says that this is going to be soluble. That means aqueous. Okay? So, this is a precipitation reaction because we have a precipitate. And I will put up some examples of the reaction types we talk about, YouTube videos done by other people. I don't really have the stuff here to do it myself. And so you can see what happens with a precipitation reaction is you have like generally two clear, colorless liquids, you pour them together, and boom, a solid forms and settles to the bottom. And generally, most solids are just kind of like white. But sometimes, you know, like lead ones could be fun colors, things like that. But you see some sort of solid form, and it settles to the bottom because it's a higher density than the water. And that solid that forms is called a precipitate. And so if that happens, you get a precipitate, you get a precipitation reaction. It's as simple as that. So let's see how you do here. All right. Let me ask you something. Does a precipitate form when aqueous barium nitrate is, mixed with aqueous sodium sulfate. Okay, so we're going to write this equation, we're going to balance it, right? So what have I got? Well, I've got barium nitrate plus sodium sulfate. And I'll pause every time I do something too. So you can pause the video if you want to take a shot at the next step, just like you could have taken a shot at that first step. But that's what we have. Now our reaction takes place. What do we get? Alright, so what do? I switch my ions, right? And so I'm going to get barium sulfate. This is a 2 minus, this is a 2 plus. So they're 1 to 1. This is a minus 1, this is a plus 1. So they are also going to be 1 to 1. Now I have to ask myself, is this balanced? And I go, and here's a trick, by the way. Here's a good trick. So you could count this like, oh, I've got 2 nitrogens and 6 oxygens, or I could just say I have 2 NO3s, because guess what I got over here? I just got NO3s. So treat polyatomic atoms like, or polyatomic ions like atoms. Okay? And so if I do a 2 here, I have 2 of these, 2 of those, I'm good, I'm balanced. So I literally had to sneak in 1 coefficient. Not bad. Alright. What are the phases going to be? So are we going to get a precipitate here? Are one of these going to be solid? Well, let's look at NaNO3. Spoiler alert, by the way. We've talked about already. So group 1 cation and nitrate, so soluble, which means aqueous. All right, but what about barium sulfate? Well, where do sulfates land? Here. So they're generally soluble, except, oh, look at that. There's our exception. Also, by the way, spoiler alert, we already talked about that one too. So solid. So yeah, there's our precipitate. So you got to switch the ions. You don't want to write the exact same stuff over here. You've got to switch them. So, you know, you just go like that. You know, they're paired, change the pairing. That's all there is to it. Alright, so what else can we say here? Well, one thing before we end the video. If there's no precipitate, there's no reaction. Okay. So, if we put these two together, I do the switch. So I go NaBr and then KCl. And this is balanced because it's all 1-1. If I look at my rules, rule 1 says that group 1 cations are going to be soluble. That's a group 1, that's a group 1. These are both aqueous. We just go no reaction. So if they stay aqueous, no reaction has happened. So all I've done is I have a container and I've got sodium floating around, I got chlorine floating around, and what happens when an ionic compound dissolves is those ions separate. So I get sodiums floating around, sodium plus 1s, I get chlorides floating around, Cl minuses. So they're floating around separately, so they're not floating around together, they're separate, they're doing their own thing. Same deal over here. I have K pluses, Br minuses, they're floating around. I pour them in together, and now they're not sticking together and making a solid, they're all just floating around. And so all I've done is mixed things together. And so we're going to talk about that more in the next video. I decided I'll break out, since this was already 20 minutes, I will break out net ionic equations into its own video. But if you don't see any aqueous, or I'm sorry, if you don't see any solids show up, if everything stays aqueous, no reaction. No reaction has occurred. You've just mixed stuff together. That's it. Alright, so we'll build on this idea in the next one. So I guess I'm kind of breaking up the topics of precipitation reactions into 2 videos, but yeah, for time reasons it makes sense. So that's what we'll do.